All right, everybody else grab a sheet of paper and start working on configurations for the following elements. Selenium, which is element 34 in your periodic table. Strontium, element 38. Iridium, element 63. Lead, 82. And magnesium, I want you to give me the +2 ion configuration, and it is element 12 on your periodic table. Because I'm out of that other paper. That's why I went to this one.
The K through Q thingy?
No, I don't. I just want the configuration, which is the 1s2, 2s2, 2p6, or you can use the noble gas cores, whichever one you wish. All right, let me get attendance, and then we'll take you guys next door. That's Olivia Morales.
Mr. Brand, are we doing a lab today?
No.
Aren't we done with labs already?
Pretty much, yeah.
Pretty much.
Well, I can't say for sure, but I think yes. I'd hate to say yes and then one come up and you'd be like, oh my God, you didn't tell us we had to do any more labs.
Yeah, so I have Mr. B.
But I do, I do want to point out, there are some people, the difference between you passing and failing this class may be what you get done by Thursday. Because there are people who are failing who are missing labs. And without them, you will fail. With them, you may not. But if you're missing a lab and you do not get it into me by Thursday, the grade will stay a 0. And even if you do poorly on the final, and then you come to me and I go, well, if you would have turned in that lab, you would have passed. And you're going to go, well, can I do it now? I go, well, you can do it next year when you take the class over again. By the way, there is no summer completion for this class. Nope. Because it's a chemistry class. It's an upper level science class. You should either pass it or not. The only way I would give somebody an incomplete is if they missed like the last 2 weeks of the trimester or something along those lines.
And I talked to Miss Matthew and got it figured out. So we're going to sell them 2 for $1. We're going to do it outside of the
16
by
unless
where
it
the
was
concession
somebody.
stand is. Aaron's going to go today and buy the popsicles from Walmart. And then I told Miss Matthew like $20, $25 for startup money should be okay because it's not very expensive. It's like $5 for a pack of 80. And then Aaron's going to buy around 200 of them for us to sell.
Awesome. Yeah.
Okay, sounds good. Because I know we have Lydia.
We'll see.
Oh my
Yeah.
God, where's SR? I can't find it.
That's why I have the numbers up there for you.
Sophia.
Oh, yeah.
And then, yeah, you two, because I want like 3 to 4 people.
Okay.
So,
Are we going to need scissors to cut off the top?
yes, we are.
Okay, sorry. If I could count, that would be a lot better. All right, Jennifer and Yvonne. Let's go next door. You need something to write with, and then you can bring all your notes. You can bring your backpack if you want, but if you're not comfortable leaving your phone there, you can put it in here. If you're comfortable leaving it there, that's fine. I don't care. Okay? Is yours in your backpack, your phone?
When I asked him, he said no one's on my desk.
Okay, and you're comfortable leaving it there? Okay.
So I just did it like normally just because
Okay.
he said you're just gonna need like the electrons that are in it, which should just be 12. So warm in here. So the school's either really hot or really cold. There's no like
That's how this whole school is. This whole school, you're either super hot or super cold.
just normal.
Thank you.
Wait,
I'm waiting.
if we're going from 4S6, do we have to do the
4S6. There is no 4S6. 4S2 maximum.
Okay.
The number next to an S is a maximum of 2. So go ahead now.
No, wait. So for EU,
Yes,
that's 63, right?
correct.
So we after we find the
So it's right here.
right. So since it's in
The 6th period here.
since it's there, do we count the 5D1?
Because you're ending in the F's, yes.
Okay, what if we put it after?
Don't. It goes before.
Before the 4F.
Before the 4, it's before the 4F's here. All we're doing is following the order set forth by the periodic table. This is first, right?
Yeah.
Then this, then these.
Okay.
Okay? Do it just like the order that it appears in the periodic table. The only time we don't do that, Cynthia, and for the rest of us, is if we're going to get all the way through these F's,
And then we come
because they fill up completely first, we would list them first, then we would go back to the 5 D's. Okay? But since you're ending in the 4 F's here, yes, you need to include this 5D1 or you're going to be off by 1 electron. Okay?
Yeah, I figured that out, but I was just wondering if we had to put the 5D before the 4.
We do, because again, it's about following in line. This, then this, then this. Okay? That's the easiest way I can describe it to you. Okay? All right. Please make sure your phones are put away and off your desks, ladies and gentlemen. We're going to get going in just a few minutes.
So we do 5D1 and then F14.
Are you ending it at 14?
No, I'm ending after.
Then you do not do the 5D1 first. Why? Because that 5D1 will be picked up with the rest of the 5Ds that you're going to put after the 4Fs. Okay, so that's the one time when we don't put it first, because we don't separate things. So you wouldn't do 5D1, 5D4 later on or something like that. Okay? Yes.
I used to be
Sophia, what can I do for you?
So if we end on like the 71 or the 103, do we still?
You still need to do that 5D1 first, or 61, because again, you're not getting back into the other Ds to where you're going to pick it up. So it is before them. You have to go all the way through the F's. If you're ending anywhere in the F's, you have to put that D1 in first. If you're getting by all of the F's, don't worry about it, because it'll be picked up later on with the rest of the D's. Does that make sense?
I think I should, right?
Yes.
Let's do Thursday.
I thought you had your hand up. Sorry.
No, you're good. I'll probably do it.
Ritzy?
I have to work on Wednesday. Should I do tomorrow? No, I was going to.
Olivia?
Here, I'll study tomorrow and do it Thursday. Is that a good idea? Yeah. Wait, because. Or should I just call him more? Like, hey, I have to do chemistry.
Olivia?
Like, I can't.
Hey. Austin?
Why'd you say Mg plus 2 ions?
Because that's what I want you to describe. Magnesium plus 2 ion.
Okay.
Well, think about what you have to do to become a plus 2 ion. And then describe,
Isn't it already plus 2 ions?
only if it's in a compound. We've been describing all of these that have been the neutral type of each of these. What if we're going to describe an ion? Think about how many electrons that ion has and then describe those electrons. Okay, ladies and gentlemen, if you want to see the answers to the quiz, please leave your pens and things and your phones at your desk. Here is version A right here, ladies and gentlemen. Here is version B right here. Version C is right over here, ladies and gentlemen. All of the answers are out if you want to go check them.
I had a.
Please, go ahead.
Wait, because the lines of purple are the right answer. No,
The lines of purple mean they were wrong.
but that's not. I circled this one and you might have.
I know. So now go see what the correct answer is.
So they're both of those answers are wrong.
I didn't say that. Now go see what the correct answer is. What I'm telling you is that question was wrong. Now go see what the correct was. A, B, C.
Do we have another quiz?
I'm thinking probably Thursday of this week.
What is that going to be on the configurations?
Configurations, atomic history, possibly Vesper,
Vesper.
valence shell, electron pair repulsion theory.
Have we learned that yet?
Nope, you have.
Oh, that's what I said.
Maybe stand on it, like tomorrow.
What?
Maybe stand on
I
it.
didn't make you, but you had. If you wanted to know the answers, you had to.
Are we learning that tomorrow?
We'll see what we see when we see what we saw.
Do you care if I come in during third or fourth hour?
Why?
Yeah.
Why does fourth indicate order?
So in reality,
What's that?
basically,
like-
you literally
Yeah.
have to basically pass.
I can't hear you. What?
So like in real life, like you literally.
What class do you have fourth hour?
I have everything down. Yeah.
I don't care. If you want to, go ahead.
No way.
Hey,
Wait, what?
are you gonna?
I'm sorry. What was your question?
I didn't know.
How does the letter between the symbol 4P3 indicate the order?
Okay, because
I don't understand the order. Anything, I don't understand anything.
well, then I really can't help you unless you're going to come in and get a lot of extra help.
And then Mr. Bright passing. Yeah.
Sure, go ahead. What is that?
And then like A because of the final. Final like A.
Which one is this?
You're gonna get a 100%.
Why? How do we know this is an S? But how do we know this is an S? What? It's eeny teeny. No. Okay.
There's only one. The little round one in the middle. That's how I know it at least.
The only shape that can have only one orientation is a spherical shape. So S's are shaped like a sphere. What's this one? This is a P, shaped like a barbell. So what tells the difference between these suborbitals? They're what? They're shaped. What is this one? A D. Again, a different shape, right? So it's the shape that tells you what is different about them. The electrons can be in either one of these places. The electrons can be in any one of these four. Why? Because they have a different shape. You want a different shape? There you go. There's a different shape. But that's the area where electrons can be. That is the best explanation we can give you, based on looking at where the electron clouds are. So, other questions off of the quiz? I'll be happy to explain any that you have. None, zero, zip, zil. Okay. 3 more minutes on the configurations, ladies and gentlemen, then we will get going. Or are you all done and ready to go? Is there anyone who needs more time?
No.
Okay, then let's move on. Good, that works out even better. Here are your configurations, ladies and gentlemen. Yes, they will be on the quiz this week. This will be the big part of the quiz. For selenium, you can use argon as a noble gas core. 4s2, 3d10, 4p4. 18, 20, 30, 34 have accounted for every electron. What the heck? Oh, sorry. I looked at the or R. I thought, where did I get O and R from? But that's the word or. Okay, I got it now. Strontium, 38. Krypton, 36. 5s2. 38. If you don't want to use the noble gas core, 1s2, 2s2, 2p6. 3s2, 3p6, 4s2. 3d10, 4p6, 5s2. 2, 4, 10, 12, 18, 20, 30, 36, 38, 38. Perfect. Questions? Europium. Xenon 54, 6s2. I did this specifically, ending in the F so that you had to put the 5f1 in, and then the 4f6. 54, 56, 57, 63. Questions?
How do you do, MG?
Lead, xenon 54 again, 6s2, 4f14. Now, why are the F's in front? Because we go through all of them. Then the D's. Then we are back into the 6P's for 2 more. Questions? Okay, so someone tell me, how does magnesium become a +2 ion? What actually has to happen to it for magnesium to become a +2 ion?
Has to be within -2? I don't know.
So no one can tell me how magnesium becomes a +2 ion.
Isn't it already a +2? It's a thing of +2.
It is in the family where it is a +2. Here you go, Jennifer. Thank you. But how does it actually become a +2? What actually happens to it?
It's with a -2.
Okay, how does something become a -2? How do you become charged?
Sleeping.
Sleeping. So this atom took a nap, woke up, oh my God, I'm a +2. I gotta go find a -2.
You eat.
Come on.
I don't know. That doesn't make sense.
What about valence electrons?
It has 2 on the left, on the outer shell.
Okay. Originally, let's talk about this. Magnesium, Mg. Without a noble gas core, give me the configuration for the 12 electrons in magnesium. What are they?
Just use the shortcut.
No, let's just do this. Come on.
2s2. 2p6. and 3s2.
Okay. Now, this is magnesium, 12 electrons, and it is neutral. This is magnesium +2. How does something become positively charged? What has to happen to that atom to become positively charged?
It
What?
has extra electrons.
You're close.
Or it has not enough electrons.
Metals do what in ionic compounds?
Gain electrons. Oh wait, no. They lose electrons.
They lose electrons. So for magnesium to become a +2,
Has to lose electrons.
how many? So now magnesium +2 ion has to lose 2 electrons, correct? Okay, how many did it start out with? 12. If it loses 2, how many does it have? So describe for me the first 10 electrons. Go.
Any.
1s2. 2s. 2p6.
There's your electron configuration. It only has 10 electrons. The first 2 are in the first energy level in the S. The next 2 are in the second energy level, the S sublevel. The next 6 are 2p6, correct? Have we accounted for all 10 electrons? Alexis keeps looking at me like I'm crazy.
I don't know. Isn't magnesium already a +2 ion? So
No, that is what I'm telling you. We are confusing magnesium atom with a magnesium ion.
Oh.
Magnesium atoms can become magnesium ions, but only can they lose electrons if something else is there that is willing to do what? To gain them. What kind of atoms gain electrons?
The non-metals.
Non-metals will gain electrons when metals lose them. Okay? Then they make an ionic bond, a bond between a positively charged ion and a negatively charged ion. Then they are stuck with each other because the magnesium has lost 2 electrons to some other non-metal that has gained 2 electrons. And they are attracted to one another. Okay? So if you lose 2 electrons from magnesium, which 2 do you lose? The 3s2, which means without these, that's the configuration for a magnesium ion.
So if it was a plus 3 charge, then we would lose 3 of the.
Okay? So now let's go to aluminum. Aluminum, 1s2, 2s2, 2p6, 3s2, 3p1, 13 electrons, correct? What kind of charge does aluminum have as an ion? Which means, how many electrons does it have?
That's 13.
10.
You have to lose electrons to become positively charged.
So you lose the amount your charge is what you lose in electrons.
Correct. But when you lose electrons, you become positive. When you gain electrons, you become negative because electrons have a negative charge. Okay, describe these 10 electrons to me.
2s2, sorry. 2p6.
Right? Right? Questions? Describe the 9 electrons for fluorine.
1s2, 2s2, 2p5.
Correct?
Yep.
Good. What kind of an ion does fluorine become? How many electrons will fluorine have when it becomes stable?
10.
Describe them. Thank you, Yuritsi.
Would always be like an exact one, like the last one in the group. So are they all going to equal their noble gas? That's right.
Oh my gosh, ladies and gentlemen, she hit the nail right on the head.
You think I'm not smart?
No, but you were the first one in the class that figured that out.
Really?
Because think about it, what do atoms want to be like when they're stable? The noble gases. So guess what? They are going to lose or gain electrons until they look like a noble gas. So sodium will lose how many electrons?
1.
When it loses that, how many does it have?
10.
Same as neon.
Wow.
Magnesium will lose 2 and look exactly like neon. Aluminum will lose 3 and look exactly like neon. Fluorine will gain 1 and look exactly like neon. Oxygen will gain 2 and look exactly like.
Neon.
So they always look like a noble gas.
Well, like, what about like the transition in the F's?
Not going to worry about it. Not going to worry about
And what about like the bottom ones, like SE, that one look like
it. SE.
34. 34.
34.
So is that one gonna gain 2 and one will look like KR?
Exactly. What would bromine do? And look like? Krypton. What would rubidium do? Lose 1, becomes a positive 1 charge though, and looks like. So the metals look like what noble gas?
The one above them.
The one above them. The non-metals look like, not the one below,
The one is their same.
the one at the end of their period. The one at the end of their period. Congratulations, ladies and gentlemen. You just found out what isoelectric is.
Yeah, I get it. This is easy. Lock in.
Wait, what'd you say this is called?
Isoelectric.
Now, before we talk about isoelectric, let's go back 1 minute, ladies and gentlemen. Let's go back to something that confused you on Friday. And that is what is called the degenerate orbital. Now, this is what explains the ones that you asked me about just a minute ago, Cynthia. Why does iron sometimes act like a +2, sometimes act like a +3? Why does copper act like a +1? Why does copper act like a +2? To be honest, they do that. This is the best way for us to explain what we already know they do.
Is it just like a random thing, or does it depend on what they're like? Becoming?
Well, it's certain charges, so it isn't just so copper can't decide one day I'm going to be a +5.
Well, yeah,
No.
obviously, but like if it's a +1 or a +2, does that depend on what they're going to be going into the ion with? Or?
No, not always, because you know what? They found that sometimes copper will react with oxygen and act like a +1, and other times it will react with oxygen and act like a +2. So that's where we get this term. It's called an apparent charge. This is what the charge appears to be. Now, scientists have to explain it. Now, here's how good quantum numbers are, ladies and gentlemen, and this whole idea of S's, P's, D's, and F's. They explain every one of those charges. They explain every apparent charge. Now, some get a little bit more creative in how they are explaining it, and I do not expect you to know when a degenerate orbital occurs. I do not expect you to predict them. But what I'm hoping is that in a few days, when I talk about the VSEPR theory, valence shell electron pair repulsion, and I tell you that carbon has a degenerate orbital, you will understand what I mean. And what I mean is a degenerate orbital is, even though there is supposed to be 2 electrons here in the 4s.
Wait, how does carbon? I thought carbon.
Just hang on. We'll get to that, okay? Even though there is supposed to be an electron here and 2 electrons here in the 4s, the only way we can explain how copper can be a +1 charge is if it takes that 1 electron and puts it over here. It puts it over here. And now there is only 1 to lose in the outer shell. So now it becomes a +1 ion. That is the only possible explanation. Why? Because if there's 2 here, it won't lose 1. That doesn't make sense. It doesn't become stable if it still has 1 electron in its outer shell, correct? This does. This explains it.
So the S and the P, like, switch.
No, it's not an S and a P. It'll be an S and like a 3D or a 5S and a 4D, something along those lines.
Oh, that's right, because they have to be like close to each other energy-wise.
Correct. Correct.
Yeah.
And the P's are way over here. Go ahead. I'm sorry. Go ahead,
So
Cynthia.
why are the S's and the P's close together in the first, second, and third period?
Well, remember, the higher up we go, the differences sometimes overlap in things. Okay? So a 4S is a little bit lower than a 3D. Okay? But not that much lower. So what we're finding is even though there's a difference in energy, sometimes they move. That's the only explanation we can give you. If they don't move here, it doesn't kick 1 into here. That explains why copper could be a +2. Why? Because we'll simply lose these 2 electrons, and now it will act like a +2 ion. Okay? It's the best explanation we can give you. And again, I'm not expecting you to completely understand it. I'm not expecting you to be like, oh yeah, this has to be a degenerate orbital here. No. But I'm expecting you to understand what a degenerate orbital is, which is the electrons can kind of move around between very close energy levels, and therefore we can get some different charges. Okay? And it only happens with these transition metals, basically. Go ahead. I'm listening.
So the orbitals have the same energy level, is that, or are they close?
They're close. That's the thing. They're
They don't
close.
have the exact same.
Not the exact same. It is actually a little bit harder for the electron to go here than it is to go here. But not that much so. So sometimes one, for some reason, gets jumped up into there. We don't know exactly why, but that's the only explanation we can give you. Okay? Questions? Okay. And again, I will explain copper when I get to or carbon when I get to carbon in a little bit. Yes, sir. What's that? This is why the transition metals have multiple charges, yes. Okay? Now, carbon does it not because it wants a different charge, Carbon does it so that it can share electrons differently. We will explain that. That's part of that VSEPR that we're going to get to. Okay? Questions? Okay. So now, here is our isoelectric. Okay? Here is our isoelectric, and we just covered this. Isoelectric is an ionic form of an atom having the same configuration as a noble gas.
Should we write that down?
No. Why? It's not on your yellow sheet. I need you to understand what this means. Because a clue on the test might be branium plus 2 is isoelectric to fermium. So you need to find out where fermium is, and branium would be 2 after it. Or maybe branium is 2 after it, and you need to go back to and find where fermium goes. Okay? That's how this would be used on your test. Okay? So what it means to be isoelectric is when an atom gains or loses electrons, and it looks just like a noble gas. So when fluorine gains 1 electron, it looks just like neon because it now has 10 electrons. When chlorine gains 1, it looks just like argon. When bromine gains 1, it looks just like krypton. Okay? Selenium gains 2, it looks like krypton. Sulfur gains 2, it looks like argon. Phosphorus gains 3, it looks like argon. Silicon gains 4, it looks like argon. Aluminum gains 5. Can't happen. Why?
Because metals don't gain.
Metals don't gain. Metals do what? Lose. So instead it loses 3 and looks like neon.
Well, like, what about like TS and everything after this?
TS. Give me a number because I'm sorry that's not one that I'm Tennessean. Where is it?
117. Or like PS,
Oh God, don't worry about it.
or anything that's underneath it after like the +4.
It loses.
Here,
Yeah, and then over.
I won't ask you about that. That's an exception. I won't ask you about it. I won't ask you about this. Why? These are man-made elements. These
But like, what about like SB? 51.
SB.
Yeah.
Okay, technically, it would lose 5 and look like krypton. I'm not going to do that to you because I don't expect you to understand all those exceptions. The ones that are solid are the +1, +2, and +3s.
It only loses 5?
Well, it has 5. That's all it would have to lose. 1, 2, 3, 4, 5 that are in its outer energy level. Because remember, these are 1 energy level below. So, okay. And really, even with these, it ain't going to happen. So if I do this isoelectric, it's going to be something over here, maybe as far as here, but that's about it. Okay? So what isoelectric means is, again, it looks exactly like neon. Fluorine, -1, has 10 electrons. This is what it looks like. Sodium, +1, has 10 electrons. This is what it looks like. Oxygen, -2, looks exactly like neon. Magnesium, +2, looks exactly like neon. The term for that, to have the same configuration, is to be isoelectric. Iso is the word that, or the prefix that means same as something. Okay? Electric is the configuration of the electrons. So that's what that means. For nitrogen, it's also just like neon, but it's got to lose 3 electrons. Aluminum would gain 3. Okay? You are always isoelectric to a noble gas. Always. Okay? Always. Okay? And you'll notice, -3 means it's still in group 15. +3 means it's in group 13. +2 means it's in group 2. -2 means it's in group 16. So any of those things could do that. Again, I'm not going to get you down in the periodic table where we're crossing that bold zigzag line. Okay? I won't do that to you. Questions?
So we won't use the D's, the D1s, the 2.
No.
I'll just use the first.
No,
places.
because here's the other thing, and this is something that you need to understand that I probably haven't explained well enough yet. This is what your test is going to look like. You'll notice there are no transition metals on here, and there are no lantanites or actinites on here. They're not on these 50 elements. These are the S and the P block. That's it.
There's not going to be
No. No. It's not going to be D's and F's.
That makes sense.
Okay, yes, it does. These are the 8 main groups of the periodic table. Okay?
Are we ever gonna add something like this?
Yes, we are. We are.
Wait, how come the D's don't want to look like the noble gas?
Because remember, they're a row behind.
Oh.
So they can't. They
It's
can't.
only the ones that are the
There's-
same.
It's only the ones that are in the outermost level that we're talking about. So those are always your S's or your P's because those are the ones that got to be somewhere between 1 and 8. The D's are not the outermost level ever. The F's are not the outermost level ever. So they don't fit into this, but that's a great point. Thank you. Questions? For sulfur, it would be isoelectric to argon. For chlorine, it would also be isoelectric to argon. For potassium, isoelectric to argon. Now, calcium, isoelectric to argon, but calcium's a +2, potassium's a +1. Chlorine is a -1, sulfur is a -2, but all of them will look exactly like argon because they will all have 36 electrons when they gain or lose electrons to become stable, because you are always gaining and losing electrons to look like a noble gas. Questions? Good. Okay. Take out your yellow sheet. It is time for atomic history, ladies and gentlemen. Many of the scientists that we are going to talk about are on your yellow sheet. I will only ask you about the major things that they did, not minor things. And as we go through this and talk about this, I will hit the major things for you. Okay? By the way, if you got a law, that's a major thing. If you found a part of the atom, that's a major thing. If you started the whole idea of the atom, that's a major thing. Okay? Only major things. Not every one of these scientists may be on your list. We'll see as we go. Questions? Good. By the way, I am sorry and I am apologizing already in advance, ladies. There is not a female on this list. Why? Because years ago, when you were studying chemistry and you found something like a discovery, proton, neutron, electron, whatever, you had to bring your discovery to a chemical review board. And the chemical review board happened to be all men. And they would tell you that your work was shoddy and that it wasn't accurate, and they would make you go away, and then they would claim it for themselves. We're jerks even back then, ladies and gentlemen. Okay? So I'm sorry there are none on there. And this is not a complete history. Okay? This isn't everybody. When did the idea of the atom start? How long ago? Okay, could you give me a year? About
1700.
1700. Anybody else?
1650.
16. Just, I'll take 1600s.
Sure.
1600s.
15.
1800s. Anybody else? What?
1200.
1500s. 1200s. Anybody else? Good news, you're only off by 1600 years.
Oh.
The idea of the atom started with a Greek philosopher named Democritus. Democritus actually gave us the word atomos, and it was about 400 BC. By the way, I will not ever quiz you on dates. Ever. Okay? But just so you have an idea, this was about 2,400 years ago. 2,400. He was a Greek philosopher who gave us what is called the discontinuous theory of matter. What does it mean to be discontinuous?
It doesn't go on.
It doesn't go on and on. And the story goes that Democritus sat down one night to have dinner. And he had a loaf of bread in front of him. And he cut it in half and he got to think, can you cut things in half forever? Can you cut them in half into smaller and smaller and smaller pieces? Or do you eventually get to some little piece that you can no longer cut in half? He said, there's some little piece out there. I'm going to call it atomos because that means indivisible and indestructible. And he gave us the idea of the atom. That's where it was born. Now, I don't know if the story about the bread is true or not, but it makes for a great story to tell. Okay? But he is credited with starting the idea of the atom. Okay? Now, there were a lot of other early Greeks who said that he was wrong. Some thought there were only 4 kinds of atoms in the world. Any idea what they were?
Hydrogen.
Nope.
Oh.
Earth, water, wind, fire. Those were the 4 atoms that made things up. Think about it. You'd set a log on fire, what happens to the flames? They get bigger, right? That fire had to be inside that log somewhere. What does the log give off as it burns? Smoke, gas. That has to be in there. That's the wind. Okay? What does it look like afterwards? That's the earth. That's what a log is made up of. They were wrong. Okay? They were wrong.
What is wood made of?
What? Carbon, hydrogen, and oxygen mostly. The stuff that's left over at the end is carbon. The hydrogen and oxygen go off into the air. Now, doesn't mean they were semi-right. They were kind of. Here's the other thing, ladies and gentlemen. A lot of the history of the atom is unknown. A lot of chemistry is unknown. Any idea why?
Because it got lost.
Oh.
What nothing to write
Everything.
Right?
so they didn't write it down.
They couldn't write it down. Why?
They didn't have a written language.
No. If you wrote chemistry down and you told people, hi, I'm a chemist, I do experiments, guess what? The church hung you. Or the church ran you out of town.
Witch.
Or they thought you were a witch practicing witchcraft or a warlock or a wizard or whatever they wanted to call it. But you couldn't go around and say, hey, yeah, I do experiments all the time. Okay? Why? Because it was frowned upon by the church at the time. So again, a lot of our history of chemistry went right out the window. So needless to say, if you came up with a medicine, you had to try it on yourself, ladies and gentlemen, because there's no one else you could give it to. And guess what? If you died, you died. Scientists died from drinking their experiments. They died from blowing themselves up in their lab. And the worst part is the next guy came along and did the same damn thing. Why? Because nobody wrote down what happened and why you blew yourself up. So it happened. Proust gave us something called the law of definite proportion. By the way, we've jumped from about 400 BC to probably about 1400 AD. Long time. Law of definite proportion says that hydrogen is the building block for all elements. And helium is actually 2 hydrogen atoms slammed together. You slam 3 together, you get a lithium ion. But he gave us what we call the law of definite proportions, which is this. When you take a compound and break it apart, there is a certain amount of this to a certain amount of this. And he was talking about mass. So in water, there were 2 grams of hydrogen to 16 grams of oxygen. That is a definite proportion, 1 to 8. And he was correct. And that's why it is still a law today. Okay? Again, we know nothing about the atom being divisible, protons, neutrons, and electrons. But we do know that things combine in a certain way. That's definite proportion. Lavoisier was a French scientist. He came along and he got to work with a new piece of equipment, ladies and gentlemen. He got to work with a balance. Okay? And I'm not talking about the digital ones in the back of the room. I'm talking about Lady Liberty holding up the balance of justice, the 2 pans on each side. And Lavoisier did experiments to disprove something. He did experiments that actually gave us the law of conservation of mass, which says that mass cannot be, it can only be changed. It can be changed into other things. Okay? He disproved what was called the phlogiston theory. See, people knew that if you burned a candle and put it in a container, eventually the candle would go out. They didn't know why. And many thought it was because there's this mythical substance in the air called phlogiston. And as long as there was phlogiston there, the candle would keep burning. Yes. But when you use up the phlogiston, guess what? Candle stop burning. Well, think about this, ladies and gentlemen. If you use something up, what does that mean? It's what? Gone. So if there's a cake there and you use it all up, you eat it all, it's gone, right? What happened to its mass? It's gone. Okay? What Lavoisier proved was that wasn't true. He did the experiments on a balance. The experiment, time after time after time after time, proved that, guess what? The mass didn't change. It wasn't that the phlogiston was used up. It was that it was changed into something else. and the mass stayed the same. Now, that's the part that you're going to put on your sheet, is that Lavoisier law of conservation of mass. What you're not going to put on your sheet, but the more important part was, how was the government of France at that time?
A little time.
Say 16, 1700s.
French Revolution.
Was ruled by
Hitler.
Sure.
Hitler? France?
I don't know.
1700s? There's a social studies teacher somewhere that's rolling over in their grave going, what in the hell is she talking about?
Hitler was Napoleon 100 years later.
The French were ruled by a king. And you had one rule if there was a king. Don't piss off the king. Because what did the king like to do to people?
Kill people.
Publicly execute them. What was the French choice of public execution? The guillotine. Well, Lavoisier thought he was getting pretty good as a scientist, and he thought he could speak out against the king, and he found out he was wrong. So they sentenced him to die by the guillotine. But there were people at the time who thought that was a very unhumane way to die. Others were like, are you kidding? Boom, cut the head off, you are dead.
Depends on how sharp the blade
So Lavoisier decided to do one last experiment, ladies and gentlemen. Because after they would chop your head off, they would pull it out of the basket and hold it up to the crowd, for the crowd to see. And Lavoisier told his assistant, if I am still alive after they cut off my head, I will give you a sign. I will blink. Pulled his head out of the basket, and the story goes that he blinked 30-some times before he finally closed his eyes one last time.
No way.
Wait, is that actually like, is it has been
Is it?
People
Has
were
this
so
been
weird
proven?
back then. They were like,
If
yes,
you-
let's
Has
watch
it been
one
proven?
with
Yes,
their
because
heads off.
actually
That sounds so
there's a
entertaining.
story, weird as it sounds, of a chicken with its head cut off
Oh yeah.
that lived for years after its head had been cut off.
It was like
Because it was cut off just high enough on the brain stems that it kept respiration, digestion, all those things moving. They used to feed the chicken with an eyedropper directly down the throat to keep it alive. They took it as a sideshow. See the amazing chicken without its head run around.
Wait, I don't know what that is.
Okay? That is a true story. Okay.
I've heard that like it's believed that like after the guillotine you can stay alive for like months.
Yes.
Well, there's people who think that now, like even after you die, your consciousness is what, for like 7 minutes or something.
Right, but they were talking physically alive in some way. Like you aren't instantaneously dead.
Maybe.
Who knows? Okay? And we're not getting into that whole discussion. Next, ladies and gentlemen, is Dalton. He is on your list. Dalton is credited with being the father of modern chemistry. Now, this is 1800s, ladies and gentlemen. Okay? Dalton gave us his atomic theory. His atomic theory had 4 points. 1, atoms are indivisible and indestructible. Who said that 2,200 years before that? So, still, about 200 years ago, thought the atom was indivisible and indestructible. Small piece of matter, that was it. Okay? Atoms that are the same are exactly the same. Exactly the same. Atoms that are different from one another. And atoms can combine to make compounds in a definite ratio, just like Proust said. But Dalton gave us the law of multiple proportions. Proust had a problem because not every time did his proportions work out. Hydrogen and oxygen were often in a 1:8 ratio. But occasionally, ladies and gentlemen, occasionally they were in a 1:16 ratio. Now, do you know what the 1:8 ratio represents?
For what?
For hydrogen and oxygen?
The
1:8.
because
Or 2:16.
the electrons.
But what was that substance? 2 grams of hydrogen to 16 grams of oxygen. Water, H2O, right?
Okay.
But sometimes we found that it was H2O2, hydrogen peroxide. Hydrogen peroxide, the stuff you put on a cut in your, probably have in your cabinet at home in a brown bottle. There are multiple ways of combining. There is carbon monoxide and carbon dioxide. A different ratio of the same 2 chemicals. Multiple proportions of the same thing. multiple proportions of the same thing. Questions?
Just took everyone's work and just said,
Most scientists did that. The greatest quote by Albert Einstein said that if I have seen further than other men who have come before me, it is because I have stood on the shoulders of giants. He admitted, this isn't all my work,
Why do you have that memorized?
because it's a cool quote. And what it says is, I use it every time we get to this unit. What it says is, he didn't come up with everything on his own, but he was able to explain things others couldn't. He was able to take work others had done. And that is why it is important that later on in this, we're going to talk about when they started actually writing things down. And now scientists actually shared their work. And now you could take what somebody else did and take it further. Berzelius is the next one who is on your list, ladies and gentlemen. He found the relative atomic masses of many of the metals on the periodic table. Metals are very reactive, and very rarely do you find them alone. So he was able to isolate metals and figure out what their atomic masses were. So again, the element named after the scientist who found the relative atomic masses of many elements is a third period noble gas. Berzelius, third period noble gas is argon. Oh, now we're cooking with gas.
Sid, why do we have to write this down on the yellow sheet when we have this when we're able to use the slideshow?
You can. Let me give you the best advice I can give you.
"Oh, just easy."
Do you want to have to go into your notes, look this up, and find this, or do you just want it in one spot where I'm telling you the main things that I'm going to ask you about that person? It's your choice. You don't want to write anything down on the yellow sheet. You do not have to, because you're right. But here's what I'm going to tell you. Even at an hour and a half, putting in 50 elements in an hour and a half takes some time. Takes some time. And the easier you have finding things, the easier it is, the quicker it is going to be for you. You're right. You can go back into your notes and you can look this up. But then you need to get off of this page to go and find out what sp3 hybridization is and what a molecular geometry of a trigonal planar is. And so good luck. Okay? Why? Did I just scare you, Alexis?
Yes.
We haven't gotten to that yet. That's Vesper. Don't worry about it. Okay? I'm sorry, Sophia?
Are you gonna ask us for all of this? So for Dalton, it's gonna be any one of those two, or just?
Well, here's the thing. Remember, laws are really important. I mean, if you got a law, that's
But
like winning an Oscar.
do we have to write down the compared metal oxide composition?
No, because that's how he found the relative masses of many metals.
Oh, sweet.
Okay? Davy, ladies and gentlemen. Davy discovered the alkali metals. The alkali metals, these right here. Okay? He found more new elements than any other person. That you probably should write both those down. Found more new elements than any other person. Hey, your funeral, go ahead. Okay? Questions? Dobereiner. I'm sorry, I asked. I'm sorry. I will slow down. All you got to do is, instead of going, just go, Mr. Brand.
Well, you
go ahead.
asked for questions.
I know, I'm sorry. But again, if I'm ever going too fast, all you got to do is say slow down. Believe me, I can go slow. I just ain't used to it. Unless I'm running.
There's so many.
There are. I'm sorry, there are.
4 slides of the history.
Yeah. We're a quarter of the way done. Can I move on to the next slide?
Yeah.
Okay, thank you. All right, next was a man named Dobereiner, ladies and gentlemen. He gave us what are called triads. He was one who made an attempt to organize the elements of the periodic table. There was not even a periodic table at this time.
So what should we write?
He created triads.
We don't have to write the 3 different.
No, don't worry about that, but understand what a triad is. A triad is he had groups of 3 elements that had similar properties. These were some of his groups: magnesium, calcium, strontium, iron, cobalt and nickel,
They're all touching.
copper, silver and gold.
That's
Did
crazy.
he do a pretty good job?
Yeah.
Probably. Probably. Okay? he was the first real attempt at organizing a periodic table. He didn't do it, but he made a shot at it. Okay? Questions? Please remember, still nothing about protons, neutrons, and electrons yet. Nothing. Atom is still an indivisible, a small piece of matter. Newlands is a musician turned scientist. And I know that doesn't seem very important, but it is because he gave us the law of octaves. Anybody? Octave? Music people?
Yeah, it makes you go higher or lower.
How many? 8 notes. Law of octaves.
There's 8.
There's 8 main periods on the periodic table. He said there was a pattern on the periodic table that
There's
8.
7.
I'm
Three
sorry,
is
8
8.
groups. Sorry, 8
Oh.
main groups. Sorry, my bad. I used the wrong term there. Thank you.
4, 5, 6.
8 main groups.
They're the 1, 2, and
They're the S's and the P's.
Yeah.
And he said that the pattern repeated every 8 elements. So there was 8 elements, boom. Now it started over again. Okay? Law of octaves. Meyer, ladies and gentlemen, is a German scientist who tried setting up the periodic table. He tried setting up a periodic table. Unfortunately for him, there was a Russian scientist named Dmitry Mendeleev who was doing the exact same thing. So it came down to whose periodic table do you like? Mendeleev, the Russian scientist, that guy was always in a hurry, ladies and gentlemen. Always in a hurry. Or Meyer. Well, they accepted Mendeleev's, but a lot of people didn't like Mendeleev's first attempt. Why? Mendeleev predicted that there were elements missing on the periodic table. Not only that they were missing, but he said, you know what, I'll tell you the mass of that element when you find it.
How do you know the mass?
I will tell you the density of that element when you find it. I will tell you the boiling point and melting point of that element when you find it. And people were like, right, so there are these imaginary elements out there that you haven't found. His periodic table really got accepted when they started to find these elements, ladies and gentlemen. And he was right about the density, about the mass, about the melting and boiling points. Because his periodic table was so well set up that he could predict those things based on looking at patterns and trends. So he gets credit with the periodic table, Meyer does not. So these two scientists who both set up periodic tables are right next to each other on the periodic table, even though their atomic number differs by 10. By 11, actually. What elements' atomic numbers differ by 11, even though they're right next to each other on your periodic table?
My periodic table? Well, like 56 and 72.
Nope, that does not differ by 11.
32 and 13.
How about 20 and 31? How
Oh,
about
because we're
38
missing the ones in the
and
middle.
49? Because we're missing the D's. We'll get into marking that special spot on your periodic table in a little bit. Okay?
Oh,
Without the D's and the F's,
Yeah.
calcium and gallium are right next to each other, even though they differ by 11.
Yeah.
Strontium and indium are right next to each other, even though they differ by 11 in atomic number. Okay? We'll get into that. Melville! This is not the guy who wrote Moby Dick.
How do you know?
Because this is not the guy.
Oh my god.
He did a Crookes tube experiment and found that different gases created different colors, ladies and gentlemen. Different gases in a Crookes tube created different colors. What's
Why
a
is
Crookes
that doing
tube?
that?
This is a Crookes tube, ladies and gentlemen. This is a Crookes tube.
We need to know.
No, but you asked, what's a Crookes tube? There's a Crookes tube. Crookes tube has a special substance on that filament in the middle. That white stuff. That, when you take and put an electric charge through it, ladies and gentlemen, something unusual happens. Let's show you.
Why do you have all this stuff laying around?
Because I'm a science teacher. I got a lot of stuff
You
laying
just
around.
know you need to use this
26 years.
Oh my god, Sophia, go touch it.
stuff. If you got one like the ball. It's green. Wait, how is it green and then it's purple?
Well, because the gas inside there, when you put an electric charge to it, causes the green line that you see going across there. Alexis, come here.
Don't touch it.
No, in front.
Oh,
Stay
in front.
Take that magnet, move over to a side. Okay? Now put the magnet. No. On the top, in the middle here. Toward
It
one
stops
end.
it.
Wait,
Move it.
like move it?
It stops the line.
No, it doesn't. What's it doing to it?
It's moving it down.
It's moving it, which means that that particle that's causing that line is attracted to a magnet. And guess what? Electricity and magnetism, closely related, ladies and gentlemen. Closely related, because electricity can make magnetism and magnetism can make electricity. There you go, ladies and gentlemen. There's your crooks too.
Can you get to turn different colors in there?
I can't because there's only one gas inside there.
Oh.
Yes.
What gas is it?
Yeah, here you go.
So what do we need to know about this guy?
That he worked with the crooks to define that gases created different colors. Millikan, ladies and gentlemen, if you thought he did some cool shit, Millikan did some really cool stuff. Sorry, that slipped. Millikan did what we call an oil drop experiment. What he did is he took oil and sprayed a very fine mist between two charged plates. And he could literally get the oil drops to suspend right in between the plates.
Go do that one now.
I don't have the equipment to do it, sorry. And then if he changed the charge, he could get the oil drops to move towards one side or the other. He could literally get them to move. He found the charge on an electron. The actual electrical charge. Okay? He quantified the charge on an electron before we even knew what electrons were. We still haven't found electrons. But both of these guys were responsible for getting us there, ladies and gentlemen. And that's where Thomson comes in. Thomson is the one credited with finding the electron. Okay? And he gave us the plum pudding model. Now, anybody in here ever had plum pudding? Good, me neither. It sounds terrible. But when I was a kid, my mother used to make chocolate pudding for us. And then right before she would serve it, ladies and gentlemen, she would take chocolate pudding, which is good, and she would put maraschino cherries in it. Chocolate pudding good, maraschino cherries good. Put them together, you got greatness. Okay, and she would mix it up so that as you're eating it, all of a sudden you would get the cherry in there, and you'd be like, "Oh yeah, this is good stuff." That's plum pudding.
According to the internet.
Anyway, they'll also nowadays call him the chocolate chip cookie model or the chocolate chip ice cream, just randomly spread out throughout. That was the idea. He thought the electrons were randomly spread out throughout the atom. But he found the electrons. He found electrons. And by the way, this is about 1870. Okay? So, what? 150 years ago? Okay? Finally found the electron.
Imagine
Okay.
how much science is going to advance in like 1,000 years.
I don't know. Maybe there isn't much more to find. Who knows?
What if we
Medicine,
found
no.
everything?
Woo, medicine. There's probably a lot of room for there. Anyone need more time before I switch this? Hey, when I was a kid, the biggest TV series was The $6 Million Man, the guy who had bionic legs, a bionic arm, and a bionic eye, and could run faster than anybody. And I don't know that we're that far off from it
Oh,
now.
the Flash? No.
She doesn't. She only listens to certain words I say. I don't get it. It's like every fifth word. Can I change this?
You said a guy who like whatever.
Yes.
Right. See, every fifth word. A guy who whatever. Thank you for emphasizing my point.
Yeah, they do bionic. Every single thing we have is bionic. So he's basically.
So basically, Thomson said the atom was divisible. It was no longer this one piece of matter. It was actually divisible.
Halfway done.
Rutherford
Where's the R?
found the atom was mostly empty space. By the way, this is like 1890s, somewhere in there. Okay? Found the nucleus of the atom. And he did it with what we call a gold foil experiment. He took gold foil, pounded it out really thin, fired an alpha particle at it. An alpha particle is positively charged. Thomson said there were these electrons randomly spread out throughout the atom. If there were, what should a negative and positive charge do to each other? Attract. But what Rutherford found was that a lot of times these positive alpha particles went right through the gold foil, never touched anything.
Because gold is metal, isn't it?
Doesn't matter.
But
If it goes right through something and doesn't touch anything, what does that mean?
they're not empty space.
There's a lot of empty space. Think about hitting a golf ball into a soccer net.
There's a lot of empty space.
And what's going to happen most of the time?
It's
It's going to go right through. Now, occasionally, maybe it hits the cords, the netting. And when it does hit them, he found that when it did hit something, instead of sticking to it, it bounced off of it. Meaning it wasn't negatively charged, it was positively. He found the nucleus of the atom. He needed to explain how the center of the atom was this positively charged part and electrons were moving around it. Guess what he used as a model? He used the solar system. He used the solar system. Now, this idea was widely accepted, ladies and gentlemen. As a matter of fact, this periodic table on the wall over here, ladies and gentlemen, is from 1930, the first year Mr. Arts graduated from East High School. Okay? Now, in 1930, they talk about planets' valence electrons and planetary electrons in completed orbitals. The idea that the electrons moved around the nucleus like the planets move around the sun was on periodic tables and put into classrooms and taught. Okay? Still,
What is it like learning that?
you'd have to ask Mr. Arts.
Can you imagine like learning new discoveries like in your classroom? Like they
You mean like coming up with a cure for an airborne disease that caused a global epidemic?
pandemic? Oh,
Pandemic, sorry.
like COVID.
What did he say?
Epidemic. Epidemic. Same thing, pretty much, just on a lesser scale.
How about the fact that, somebody invented a computer that you can have in the palm of your hand
And did you see how big
and make
gold
call.
But
Yeah.
like, imagine you're in school and they're like, "Wait, we actually have a new periodic table, so this one's wrong."
Don't worry, someday that one will probably be wrong, so will that one.
How old?
I doubt that will be wrong, but there will be more than just protons, neutrons, and
Oh my god,
electrons.
the bomb's about to ring, guys.
Oh my gosh, we got a minute and a half. Bohr proposed a quantized electron. Any idea what quantized mean?
Amount.
They have a certain amount of energy. Certain amount of energy. Okay?
But
And
then,
that the electrons were not orbiting the nucleus like planets, that they were in energy levels. They were in energy levels, ladies and gentlemen. Okay? And tomorrow you're going to have to remind me that we left off with Bohr.
okay.
Questions?
No, sir.
Heisenberg.
Ooh, he wasn't sure about things.
So he was crazy.
Nope, he just had an uncertainty principle.
So then why is he famous?
Because he had a principle. Now, a principle is not a law. So law is like winning an Oscar. He like
Literally
won
called the uncertainty.
like a Golden Globe.
A golden globe is still good, isn't it?
I understand that, but it's no Oscar.
Jeez.
Actually, aren't they just like they're just different awards for different categories?
Correct. But
An
people know who
Oscar-
wins the Oscar every year. Nobody knows who wins the Golden Globe.
Isn't the Golden Globe for music?
For music, theater, things like that.
And then the
Musicals.
Oscar is for acting.
Acting, film acting normally, yes.
Then there's another one.
Then there's the Emmy.
Oh yeah.
Yeah, I mean,
And then there's a Tony.
oh yeah, I forgot what Tony's.
So again, ladies and gentlemen, time is running out. You have 3 days left after today to get any missing work in and retake Unit 7 test if you are interested. And since no one has shown me any corrections yet or talked to me about a retake, I figure it's going to be an easy week for me.
Brand, how do you feel that Nuggets actually lost it?
Actually, you know what? I'm very surprised by the NBA this year because teams that basically aren't super teams are actually winning, so I'm kind of happy about that.
That's
Why do they mix them?
crazy. Like me.
Why?
That's me East
The
next
Knicks
year.
are cool.
Nah, I'd rather see the Celtics before the Knicks.
Why?
The Knicks have been cursed ever since Jordan came along when he stopped.
Why?
them from
I have
winning.
been terrible on every. Like I have gotten like 70% of every single one of my history tests.
Farhan will
Just
pick
got
a
my
team
team
now
Friday.
that's still in it,
100.
and when they lose,
23
he'll
and
pick a different
25.
team that's still in it until that team loses. And then they'll pick a team
I'm
for
so
next year.
happy. With Benjamin.
You have the Celtics?
I called him last night.
It's not credit.
So how do you prove it?
I like
He said, "Give him like doing it all, Celtics doing it
How do you
all."
what?
How do you prove
A
which
plus.
other?
I'm taking A plus.
I love him.
I
I
want
want
to
to
take
take
his
his classes.
But A plus was so long.
Well, I'm glad we could have this conversation, Cynthia. Hey, how can I say this nicely? Get out!
Wait.
No, get out!
I'm gonna do my test tomorrow.
You haven't shown me any corrections yet.
I'll do it today. Actually, I already started.
Well, I need them before you can take the
I'll do
test.
it after school.
I still need them before you can take the test.
I know.
So if you turn them into me tomorrow, you can come tomorrow after school and take the retake.
That's what I'm telling you.
Mr.
Okay, and I'm agreeing with you, but I'm just letting you know that I need the corrections tomorrow in class.
I
Okay,
can't work. I mean, because I work the whole week besides tomorrow.
good, excellent,
Unless
wonderful.
I start during lunch.
No, sorry, I ate lunch. Look at me.
I
Look at
can't
me.
go over there.
No,
Damn, I'm gonna take like fucking. Oh, sorry. There. I'll take like 2 hours.
How do you
doing
know?
the test.
you haven't even seen the retake yet.
So what are you trying to say that it's harder? Or that
No.
it's easier?
But I make sure you know the material.
Well, I know.
Okay, then you won't
I
have a
could have
problem.
gotten a good score. I just didn't answer 2 problems.
Okay, you won't have a problem like that on the retake.
It's just, the,
give her two.
it's just a balancing where I sometimes mess up.
Well, I guess we'll find out when you do the retake. Okay, have a good day. Don't be late to your next class because I'm not writing you passes. Go.
I'm not.
Liar!
It's because she has lunch. I have class.
I know, go.
How do you know?
Because I had to write you a pass to Miss Sutter the one time and then you didn't even use it.
Work.
Get out! Get! Go! Go away! Goodbye! Have a good day. See you later. Adios. Arrivederci.